Hi everyone. For our final project, we explored different approaches for measuring image similarity. We worked with a feature-based method using ORB and a structural approach called image structural component analysis or ISCA. ISCA is designed to capture perceptual similarity by analyzing the structure of image blocks using SSIM. To help support and explain what ISCA is doing, I also use PCA as a simple reference. The goal was to show how ISCA builds on structural information, not to compare the two directly. This is an example from tiny image this data set. On the left is the original grayscale image, and on the right is its PCA reconstruction using 100 components. PCA works by finding directions of maximum variance across entire images. It captures broad features but often loses fine local structure like texture or edges. That's why PCA is useful as a baseline, but not sufficient when our goal is to match how humans perceive a structure in images. This leads us to ISCA, which learns on blocks of the image using SSIM. So what is SSIM? SSIM stands for Structural Similarity Index. It compares images not pixel by pixel, but based on the local structure, contrast, and luminance. This makes it much better proxy for human perception. For example, even slightly blurred image may look like plus the SSIM can reflect it. For example, the left image, as you can see, is the reference image and the middle one has slightly shifted the square part. But despite the shift, SSIM maps the right shows high similarity, especially around the right square. This illustrates that SSIM is robust to small shifts and captures structural content better than pixel-wise difference. So these slides show how ISCM works on one image. This image is first divided into small 8 by 8 blocks. Then each block is projected into a special space and captures its structure like edges, corners, and textures. What you're seeing is a heat map where brighter squares mean that block has a strong structure and darker squares mean it's more plain. This tells us which parts of the image carry more visual information. And ISCA does this block by block to focus on the image's structure, which is important for us. What we have done, we have started by pre-processing the tiny ImageNet dataset, converting each image to grayscale and resizing it to 64 by 64. We first trained the ISCA model using a small subset of 20 test image to verify functionality, then scale it to the full training set. Each image was divided into 64 blocks, 8 by 8 pixel. For each block, we trained orthonormal basis using SSIM-based loss and ADMM optimization. We also implemented PCA on flattened image, but only as a supporting reference, not for comparison these two methods. In this slide, you can see the overall results of the methods. In figure 4, both ISCA and PCA hover around 50% accuracy across all thresholds. ISCA is slightly improved near a certain threshold, but it's minimal. And PCA fluctuates early and then flatten at 50%. In the figure 5, you can see that it's correctly classified 482 dissimilar pairs, but it fails to detect similar pairs, only correctly classifying one out of 482. This result is high for the true negative rate, but very low sensitivity for true positive, leading to poor F1 score for similar class. So in this slide, you can see the similarity evaluation, and for better fun score, we have implemented data balancing, which was not really helpful, but the results show that ISCA and PCA captures poorly in this kind of picture.
So then the next method I chose was oriented fast rotated brief, aka orb. I chose it because I thought it looked cool, honestly. This is a geometric feature extractor for detecting corners, and to understand why it was created, we need to look into a history of feature extractors. At the time, there didn't really exist a feature extractor that was both robust and could handle real-time applications. There were the Gaussian-based feature extractors like SIFT and SURF, but these were both patented and also they weren't very quick. They were too slow for real-time applications, but they were really robust. And then on the opposite end, we have two extremely fast algorithms that were open source, and their combination is actually the backbone of Orb. So fast finds areas in an image where there are high intensity changes, essentially corners, and but there's no context to these corners outside of the image. And so if you scale up or rotate the image, you no longer know where the key points should be in the altered image. Then we have brief. This takes a group of pixels and chooses a few to compare if one is brighter than the other, and then store those comparisons in 256-bit string. Because we aren't recording brightness levels, but rather if one pixel is brighter than the other, it makes the model invariant to brightness. But it's still going to be sensitive to in-plane rotation. So to fix these, so most of fast issues can be fixed using Harris corners. This is a way to score an area based on how corner-like or how edge-like it is. And now that each key point has a score, we can map out the key points based on that score, and we can size up or down the image, and we still know which key point is which. Then we use an aggregate of different resolutions to make like scale robust model from that point. It's a scale pyramid. Then OFAST was created by using the center of those Harris corners, and we drew a vector to each key point's center of brightness. And then so that vector has distance and the angle. And with those angles, we have a way to record the key point's orientation. Then to fix the drawback of brief, they created something called steered brief, where they rotated the area to match the pixels. The technique had a tendency to over-rotate, meaning like rotating things that to match that shouldn't match, making it worse in rotation than like the original brief. So they used pixel comparisons that weren't sensitive to rotation, and then they rotated them 30 different ways and recorded that in a lookup table. And this solved the rotation problem. And so the combination of all these created a corner detector that was robust against rotation, scale, brightness, and that was also fast enough for real-time applications. And this was Orb. So for our model, we used Orb and we used the classic k-means and bag of visual words combination for classification. This uses k-means to cluster similar key points together into what's called visual words. Orb generally uses key points ranging from 500 to 2000. However, for this model, we ended up using like all the key points from 32 to 2000. And we every time we just got this degenerate solution with a 99.5% accuracy, meaning the model was calling every pair dissimilar. And here, like you can see, the accuracy threshold kept being 99.5% and similar distribution, like it's all dissimilar. And so the techniques we try to fix it, first we tried balancing the splits. Um, it didn't help too much. We added a spatial pyramid where we split the image into a grid which holds the key points in grid locations to like help spatial information. That wasn't too helpful either. But what was really helpful was we started using soft assignments instead of hard quantization where like words are like word is only assigned to one feature. We could assign partial word assignments to features. And so like it just gives you more discrimination. And we were able to leverage this using LDA, which is a machine learning technique. We also added more diagnostic tests to see if there would be any like future problems or this wasn't like these don't solve any of the problems. And so as you can see, the data still sucked. We had a 23% accuracy throughout like all max key points that we changed the parameters from 32 max key points to 500 max key points. And we still retain this consistent like around 23% max accuracy and a negative similarity threshold for it. The ROC curve was also always like close to that middle line, which means it's not much better than random chance. We have those balanced pairs, as you can see from both the graph and from the bottom of the hyperparameters, where the pairs per class, we have 2,000 similar pairs and we have 5,000 different pairs. But precision, ROC, accuracy, threshold. It's all horrible. And so maybe the problem is that the bag of visual words is just taking too much spatial information away. So the solution would be we just lower the class count. And so we tried lowering the class count. We lowered it all the way to 10 class limits. And like clearly there's an improvement. Accuracy jumped to 40% this time. And that ROC curve is looking less like that straight middle line. But it's still pretty terrible. We still have a negative threshold and we still have very abysmal precision. Um, so what would be the issue then? We're trying to think, and it's probably has to do with the tiny images themselves. I mean, these are geometric features that they're trying to extract, geometric corners, and these images are such low resolution that there's nowhere for like proper corners for the orb to anchor onto. And so we tried testing that. And we did. We ran a key point drawing test and we did that on multiple images. And we found what's shocking is that there were some images, even at the lowest fast threshold for detecting corners, they would just detect zero corners whatsoever. And so this just means that the resolution was so bad that even at the most lenient, there's no corners possible. And with that, if you don't have enough corners, then you're just not going to be able, the data set resolution of 64 by 64 is too low. There's never enough key points to do proper classification. And we saw this not only for OR, but we kind of saw this for ISCA too. And so while these traditional methods are very fast and don't require much training and can be very powerful, as you can see on these really low resolution training and test sets, they're just not reliable as the data, the models like the CNNs that we see from other groups. Thanks for our attention. Thank you.